I decided to upgrade my CNC 6040 to a closed-loop system. My existing arrangement had an upgrade when I went over to Windows 10, and this included a UC100 USB to parallel port and a Gecko 540 controller. This is a new combination. The selection was a package deal around the same size motors as my existing setup. So I have Mach 3 running on Windows 10, a UC100 USB parallel port interface unit, LCDA 257S closed loop stepper motor controller, and LC57H 276 NEMA 23 stepper motors, each with an integral encoder. As I did the upgrade, I realized that you now have to look a lot harder at every parts of the CNC system than I had to do before, especially kernel speeds, the total maximum velocity, and the pulses per revolution settings on the closed loop controller. So let's look at the components in turn and see how they're interrelated. The kernel speed of the Mach 3 can be set to one of 5 settings between 25 kHz to 100 kHz. This is the maximum frequency that the step pulses can be sent out of the parallel port. The manual says that at 25 kHz you'll get about 750 RPM on a 10 microstep controller on a standard 1.8 degree stepper motor. Okay, a little sidebar here. How did they determine this? The table shows the calculation using the parameters the Mach 3 manual has given. What we can see is that there is a maximum speed of motor rotation that depends on the kernel speed, and this of course limits the velocity of travel. There are many references to closed-loop controllers on the net, including their advantages over open-loop controllers. There are also many references to motor encoders. I suggest you read up on both of these if this is all new to you. In basic terms, the number of pulse steps to turn one revolution is determined by the pulse per revolution setting on the closed-loop controller. So if you have set 2000 pulses per revolution, then you need 2000 pulses to turn the motor one full revolution. Sounds easy, eh? Well, this is not as easy as it seems. There are limitations, as we will see, and questions to be answered. But before I can show you these limitations, we have to have a quick look at the other systems in a CNC. Stepper motors eventually drive a gantry or a spindle motor. Most small CNCs have a direct drive from the stepper motor to the lead screw, and the pitch of the lead screw may be different on different axes. There is very little information provided on the ratio for motor turning to linear displacement for small systems that I can find. Yet this is a critical factor in setting up a closed-loop controller. This screenshot is from a manufacturer of a lead screw. No pitch information is shown, but plenty on the length and diameter options. The problem is that we need this information as part of our setup. The motor specification states that the encoder line has 1000 parts per revolution, which I read as 1000 discrete sensing locations on the encoder per revolution. We can see from the wiring that there are 2 encoder transmitters per encoder wheel. This arrangement is common and is called quadrature sensing, and allows the sensing electronics to determine more physical locations than the 1000 positions in the one encoder revolution. With quadrature sensing, the leading and trailing edges of the sensor pulses are measured, and it is relatively easy to determine the position to 1/4 of the number of discrete sensing locations. So the controller can easily determine 4000 physical locations from the 1000 line encoder in one revolution on this motor. The LCDA has a bewildering array of pulses per rev settings available. They range from 800 to 51200 and are settable by 4 dip switches on the unit. I can find little information on the LCDA, but a manual I have for the CL57T, this range adjustment is called microstepping. Now, traditional microstepping is a method where the current is adjusted on the motor coils to change the torque and hence the rotor position. The maximum is usually 256 divisions for each step, so 256 pulses by 200 steps gives 51,200 microsteps for every revolution. But if you use this technique, then you're using coil currents to hold the position, not the encoder. The ULR reference is a great article on microstepping testing. So for me this raises some questions. Is position attained with just the sensors? Is there some interpolation used to determine actual position? Is traditional microstepping used for controlling motor current? Why is there the recognizable 51,200 factor if only the encoder sensors are used? Is it a combination of the two? If only sensors are used, How do you interpolate sensor position between 800 positions to 51,200? How accurate is it, and how repeatable? If it uses traditional microstepping, then how can you say with certainty that you don't lose steps with this closed-loop controller? I can find no published information on how accurate or repeatable closed-loop controllers of this type are at high PPR settings, nor finding any information on the methods actually used. Unfortunately, I don't have the measuring equipment to test all of this. Hopefully someone out there knows and can tell us. It would be good for someone to demonstrate whether you really do get high precision accuracy by selecting greater and greater PPR values. Okay, let's look at something else. In the motor tuning section of Mach 3, you can determine the maximum velocity in inches per minute or millimeters per minute. So the step pulse frequency required is determined by the ratio of the motor turns to linear movement and the maximum velocity you have set. Let's look at the math for a couple of examples. A is the velocity we set in the Mach 3 tuning. B is the ratio of the motor turns to linear movement, in this case quarter of a turn for 1 millimeter. C is the pulses per rev set on the LCDA, and D is obviously seconds in a minute. And the step frequency is given by the simple formula A times B times C divided by D. The tables show the frequency of the step pulses for two conditions. Both are well within the kernel speed of the Mach 3, the UC100, and the input frequency limit of the LCDA, which is 200 kHz. Again, as a little sidebar, we can manipulate the above formula to provide some other interesting information, such as the total pulses needed to move any distance and the actual turns per millimeter ratio of the motor and lead screw, or the velocity. These formulas you can easily set up in Excel or something similar. The UC100 takes the strain off the PC running Mach 3 by buffering the commands, and according to the data sheet can output steps in three kernel ranges, 25, 50 and 100 kHz. These are the only kernel settings that can be used compared with the 6 ranges available in Mach 3. The LCDA can accept pulses up to 200 Hz, so there are no issues connecting to the fastest output of the UC100. Okay, we have looked at the bits and finally we can get to the real part. We have 4 interrelating factors to set up or to know. The ratio of the motor turn to linear movement on the actual CNC machine, pulses per revolution set on the LCDA, the motor velocity we set up in Mach 3, and the kernel speed of the UC100, or the Mach 3 if you connect directly to the parallel port. The following 3 tables show the step frequency required for the velocity and the pulses per rev you select, the kernel frequency that you have to select, and the limits of the kernel frequency for the above selections. Each table has a different turns per millimeter figure, and I've chosen 0.25, 0.5 and 1 turn per millimeter just as a wide range to demonstrate the limitations. This table is for a motor lead arrangement where the motor rotates a quarter of a turn for each millimeter of linear movement. The 2 left-hand columns show the velocity in millimeters per minute with a conversion to inch per minute, and the table row values show the frequency of the stepper pulses required for the pulses per rev set on the LCDA. The coloured areas show the outer limits of the kernel selections for 25, 50 and 100 kHz. You can see at the 40,000 pulses per rev setting, you can only select up to 600 millimeters per minute velocity. I didn't bother with the 51,200 volt range. The formula for each cell is the same as the first formula I gave above. This is the same again, but this time for motor travel over half a rev per millimeter of travel. The selection of pulses per rev becomes more restricted. And again, for a high geared motor with only 1 rev per millimeter of travel, you can see the pattern. The higher the gearing, the lower the pulses per revolution that you have to use. It is clear that when you use a closed loop controller of the type I have chosen, you have to take into consideration many more factors than a simple open loop controller. You can see that the pulse per revolution settings greater than 20,000 would be a little practical value as you run out of kernel speed. You can see the impact of the gearing to the lead screw. And you can see that for me there are still some unanswered questions on the control of the LCDA. Hopefully someone can answer these. Well, before we finish, I thought I would show you my settings and a schematic of how I put it all together. These are my settings. 4,000 pulses per rev and a maximum velocity of 1,000 mm per minute works okay for me, though long travels seem to take an age. My motors move at about 1/5 the rev for 1 mm of movement, or about 0.2 turns per millimeter, and the Z is different than the X and Y axis. So why have I chosen 4,000 pulses per rev? Firstly, it's a finite calculation for quadrature encoders. It allows a finer control than, say, the 2,000 pulses per rev setting. A low kernel sleeve can be selected, and a high maximum velocity range without changing the kernel speed. This is a wiring diagram for my setup. I use an interface relay for the spindle motor on-off control and manually set the speed at the moment. I have a 5V LED cluster on the spindle motor to eliminate the work. I stripped the original control box and added the new controllers, salvaging the case, power supply and buttons, etc. Well, I hope this has all been of interest. I'd be pleased if someone could explain how the high PPR rates are developed from only 2 sensors on the encoding wheel, or if current microstepping is also included and how it works with encoder.